Here's a couple of slides on what is real science. Take a few minutes, pause the video if you need to, and think about what you think real science is. For me, real science is very, very different than the way it's portrayed in textbooks. Textbooks often present a series of science discoveries as a history, really, the history of the discoveries in whatever topic it's covering. And it may seem to someone who doesn't know very much about science like it's a never-ending series of right answers. But real science is very different than that. Real science has a ton of dead ends and blind alleys and false starts because we're struggling to figure out what the right answer is, and we don't always know how we need to find it. Science problems, as presented in textbooks, have very, very clear answers and very specific methods you're supposed to use to find the answer. So you could put 1.2 as the answer to your test problem, and the teacher could mark you wrong when the answer of 1.3 is right. So they're very, very specific, exact answers. But real science is very different. It's not exactly made up as you go along, but different people solve the same problem in very different ways. And many answers can be right. You can have 1.2 and 1.3 both be right depending on the measurement error of the thing in question. So in real science, the only way that you know it's the right answer is if you understand each and everything that you did, and if you believe that each and every step that you did to get to your answer is the right thing to do. It is not the same thing as there is no right answer, but it is the same as there is no answer in the back of the book. And what this means is that wrong answers get published because the authors believed everything they did to get there was right. And subsequent investigators come through with either a better method or better data or a better approach, and they might find the right answer using that different approach. So at least when I was in school, the kind of labs that we had were very canned, like my first bullet here. When you sit down to do it, you or someone, maybe your teacher, knows exactly what the answer is going to be before you even come into class. And you or someone knows exactly what you're supposed to do to get that answer. Hit this button, read out this number, and write it in your notebook. Probably there's a cookbook, a very specific cookbook provided with your lab that says set it up this way. Moreover, everyone in your class and the class before you and the class before them does exactly the same series of steps. And you probably went through the steps just once. And you may not have understood why each step was important. And you have to write up your report in a very formulaic manner. It has to have a title, purpose, materials, procedure, conclusion structure to it. Or I've heard of some places where scientific research is presented as going to the library and summarizing what we as a species already know about a particular topic and writing up a term paper, sometimes called a research paper. But real science has nothing to do with that. Real scientific research looks totally different. So real research looks more like this. You have to think of your question. It can be an entirely new, innovative question or leveraging off another project. But then you have to write a proposal to get whatever resources you need, whether that's money or telescope time or supercomputer access or lab space, whatever it is, you need to get those resources in order to do it. And because you're wandering around literally on the forefront of human knowledge, you really need to understand each and every step. And you need to really believe that each step is exactly the right thing to do. But more often than not, it isn't the right thing to do. Sometimes you have tools or code or an approach from another investigation you've done that you can apply. And sometimes those tools work and it's easy to move forward. But pretty often you have to modify the tools you have or the approach, or you have to design something totally different that's going to work to answer your question. You have to spend an awful lot of time making sure that whatever you're doing is not affecting your conclusions adversely. So for example, since I'm an observer, I'm an observational astronomer, I want to make really sure that what I'm doing is not introducing something that we call artifacts. And I have to make really sure that I'm not accepting instrumental artifacts as real. And I need to make sure that the data really are representative of reality. And the result of that is I don't think I've ever reduced data just once. They're more often than not, I reduce it 2, 3, 4, 5, 6 times, trying to make sure that every step I've done is correct. So I have an example here of what artifacts are. Here's a picture that I found on the web of a high school football game at night. Now, based on your own experience, that these very bright field lights are not gigantic fuzzy blobs with weird purple halos coming off toward each other and red halos on the other side and spiky things coming down. From your experience that that's not real. That's an artifact. That's a result of how the camera plus the camera's detector responded to the lighting situation, where the person taking the picture wanted to make sure that they could see the action on the field. And so the lights are hugely overexposed. So the same kind of thing happens in astronomical data, where there's artifacts, there's things that are a result of how the detector is seeing the light, that you cannot then go off and write a paper about how you've discovered giant purple blobs floating above the players at this high school football game. So in the process of doing that, it really, really helps to talk about your results, talk about your approach with colleagues and get feedback. Hey, I did this. Do you think that's the right thing? Or how am I going to solve this? Do you have any suggestions? In the end, you have to redo it again and again and again, as many times as it takes until you're absolutely sure it's right. And it could very well be that even if you've invested days, weeks, months, even years of your life into something, it may be that it's a dead end. It may be so totally incorrect that you can't even publish it. So all you have to do is walk away. There's nothing more that you can do. And it's hard when you've put in many, many, many hours and weeks and months into something to go, well, I guess it's a dead end. But it happens. It's happened to me. It's hard, but that's what you have to do. If it's not right, then there's no sense in pursuing it. But if it is right, if you do think it's okay, then you do need to write it up carefully and submit it to a journal. Nobody is going to write a paper that has title, purpose, materials, procedure, conclusions. There are going to be some structural similarities. Every paper is going to have an abstract that summarizes the main points. Every paper is going to have an introduction, which sets up why you did the study. Every paper should have a discussion of, in my case, how you got the data and what you did to it. Or, in your biology lab, how you set up the experiment. Some basics. But then after that, sort of the gloves are off. You can do whatever you want. You can set it up to explain what you did in whatever way most makes sense to explain what you did and how you came to those conclusions. And then the last section of the paper is usually a restatement of the conclusions that you've come to. When you submit it to a journal, what happens is the editors of the journal go and find peers. In other words, other PhD astronomers, preferably someone who does something close to what you're doing, to read the paper and send back comments. Now, most of the time, that is a blind peer review. That is, I submit a paper, and the editors have to go find someone who's not a co-author of my paper, who does not co-author too many papers with me. In other words, they're not a close collaborator, but someone who does similar science to what my paper is talking about. And then they ask that person, and the person either says, yes, I can do this by this deadline, or no, I'm sorry, I can't, you need to find somebody else. So the editor finds someone who can do it, and then the editor collects the comments from the person and then sends the comments back to me. I don't know who that person is unless they choose to tell me. And that, in theory, is supposed to provide a forum for more honest critique about a paper. Sometimes, most of the time, astronomers and scientists in general are scrupulously honest. Sometimes it fails. Sometimes you get rude response, and the editor is supposed to intercept that. But most of the time, they're really good comments. I think only once have I had really awful comments. All the other papers I've written have had really thoughtful comments from my peers saying, hey, did you consider this effect? Or, I don't agree with what you did here. Or, it could be that it's not, when you get to this point, is when you find out, oh, rats, somebody else already did this. Or, oh, man, this is a complete dead end based on what the peer review says. And that's why this process works. Once you get your comments back from the referee, then you have to respond to the comments, and the editor decides, have you responded sufficiently or not? Then your paper can be published. And then you can begin again, coming up with another question. Because this process takes time, Scientists are usually working on many different projects at once, in addition to their other duties, such as teaching classes or supporting spacecraft and archives like I do. So, what are the differences between scientists and engineers? Think about that for a minute. Pause the video if you need to. So for science versus engineering, the way I think of it is engineers build things, scientists learn about nature. So it turns out there's a continuum of individuals. There are plenty of people who are engineering scientists and scientific engineers. There's really a continuum of individuals. But there really is mostly two populations and two cultures. So for example, JPL near Caltech has a lot of engineers, and they love their 8 a.m. meetings. Oh my gosh. If they have a choice, they'll have a meeting at 8 a.m. Astronomers hate that. I know some astronomers who have perfected the art of calling into those 8 a.m. telecons while still being under the covers in bed. So there is two different cultures really between the scientists and the engineers. NASA as a whole, not just JPL, but NASA as a whole has a lot of both, but they do have more engineers than scientists. And the truth is that really good missions or telescopes or other facilities come when the two groups work really well together. So for example, if you want to build a spacecraft that's going to smash into a comet so you can tell what the comet is made of, you as an engineer have to work with the scientists to figure out what is okay to make that impactor out of. Because if you make the impactor out of the same stuff that they think is in the comet, when you measure the results of that collision of the impactor into the comet, you will be confused about what is coming from the impactor and what is coming from the comet. So really good missions have to come from engineers and scientists working very closely together. So are scientists and engineers creative people? Think about your answer. Pause the video if you need to. Yes, scientists and engineers have to be very creative people. So the example that I like to think of to demonstrate this is the question of, could life have existed on Mars? And how would we find out? Well, the scientists go away and think, and they come back and they say, okay, life as we understand it needs water. So we need to look for water now or ever in the past on Mars. So the best way we can think of to do this is to send a rolling robot geologist to Mars that can handle all sorts of the rocky, rough, steep terrain. And it's going to need tools so that it can drill into rock, vaporize bits of rock, read the chemical signature of the rock, and take lots and lots of pictures as it's rolling around. That way, we will figure out whether or not Mars was ever wet. Now, the engineers take that information and go, oh my goodness, you want to vaporize rock? Holy cow. Okay, so in order to do that, we're going to have a nuclear-powered machine, and with all your other requirements, it's going to be the size of a small car. We need to figure out how to get it safely to Mars and safely on the surface of Mars. So it needs to fit inside of a rocket and unfold totally on its own when it gets there. And the best way we can think of to get the thing onto the surface of Mars without damage either to it or the science it's likely to do is to have it lowered from a sky crane gently onto the surface. And it needs to be able to drive itself within reason, because we don't have real-time communications to Mars. You can't sit with a joystick and control it. So the rover has to know what to do if it's facing a big rock or a chasm. You can imagine that creativity is absolutely critical to being able to do all of this. So here's a video that comes from the Mars Curiosity team. It's all artists' conceptions, but it shows you how the Mars rover Curiosity got to Earth. That's still in Earth orbit. It's leaving Earth orbit. It's jettisoning part of the rocket that got it up there. So there it is, leaving Earth's orbit. It's on its way to Mars. So when it gets to Mars, it kicks off part of its spacecraft, and then it has something called a back shell, which is helping it get through the atmosphere without burning up. So then it gets down to the surface of Mars. It's going to eject the back shell eventually, but it also has to deploy a parachute. There's the back shell going away. So it deploys a parachute to slow it down. Then this thing has to fall out, and it's got these jets that keep it suspended above the surface. And then it lowers an unfolding robot onto the surface very, very gently, drops it off very, very carefully, and then flies away so that it doesn't impact the rover. There's the nuclear power parts of it, and there's Curiosity rolling around on Mars being a robot geologist. And the video continues to show that it's rolling around. I think it's going to laser a rock here. Let's see if it's going to do that. There we go. It's vaporizing bits of rock, and it's going to measure the chemical signature of the part of the rock that it vaporized. So this is a very sophisticated system, And you have to be creative in order to build it, to figure out how to get it there, and to figure out what you're going to use it for, why you built it the way you did when it gets there. So for specifically this rover, most of the engineers' work was in getting the rover to Mars and having it be working when it gets there. So there was lots of engineering work building it and testing it and getting it to Mars. Now that it's there, there's not a lot of work for the engineers to do. Most of the engineers have gone off to work on the next project. Many of them have gone off to work on a submarine that's going to go to Europa. So there's relatively little engineering happening now because the thing is built and working. Scientists, in contrast, were not terribly busy during the building and testing. They advised engineers, like, we need it to do this, and no, you can't build it like this, it has to be like that, and along the process of building and testing. But they had very little to do until the rover got to Mars. Now that it's there and working, the scientists are super busy using the rover and learning about Mars. So that's the difference. Engineers build things, scientists learn about nature.